Hello viewers of mine, this is another What the Physics video. This one is on the work energy theorem. But before we do that, of course, we need to summarize the conservation of energy, or specifically mechanical energy. And you say, well, what is mechanical energy? Well, that's worth going back and watching the video. But things that you should be writing down in your notes would be something along the lines of, oh, look, I can use bar charts to help me visualize the different types of energy at the different moments. We can go from one type of energy to another, to another, to another, to another, to another. Maybe not quite that often, but from one to another. And I can represent how much of any type of energy there is with the size of the bar chart. And then I can use that to help me make the equation for conservation of energy. Oh yeah. Oh yeah. And you know what, folks? Sometimes we incorporated work in there, and really that's what we're going to be focusing on right now. The work energy theorem. It says I can, and by it I mean the learning targets, I can incorporate work with change in energy and model it with bar charts. And I can mathematically solve the different concepts in and acting on a system. Woo! Woo. The work energy theorem says, or excuse me, it is saying that work done by an external force is equal to the change in energy of the system. Now, whether the system is one object or multiple objects, that is not really the point. If there is some object that is doing that is exerting an outside force on the system, so this object is not part of the system, doing an outside force acting on it, and then we've got the displacement in the correct direction and such, then that can change up. And by change up, I mean it can increase or decrease the energy of the system. That means we can have a change in the kinetic energy, or the spring potential energy, or the gravitational potential energy, or the combination of all of those. I just marked it as potential and kinetic, but you know, there are different flavors of potential energy. So here's the kinetic energy. We'll start with that. So when an object is speeding up or slowing down on a flat surface, the work is equal to the change in kinetic energy. So we know that if we're going up and down hills, we're going up a hill, we typically slow down. That's because we're changing kinetic into gravitational. We go down the hill, all right, we speed up, we change gravitational potential energy into kinetic energy. Sure. But what about if we're going along a nice flat road and you let up on the gas and you're just cruising along? You should just keep cruising along at that speed forever and ever, right? But you don't. You start to slow down. Why is that? What's slowing you down? Well, there must be some type of work being done on you, taking away some of that kinetic energy. Or if you want to speed up, you can push on the gas pedal, and that is implying that the road is pushing on you more and more. And that gets a little more complicated, but it's the friction on the road. Anyhow, that will give you an increase in the kinetic energy. Point is, we can go faster, and if we're going faster, that means we have a positive work is done on the object. And then if we're going slower, that means negative work is done on the object. So that's a turtle with a rocket strapped to it. Yeah, be careful. That's going to be going crazy fast, right? And then for slowing objects down, okay, that means we're talking about, well, of course, it's the Matrix, you slowing down the bullets because he doesn't need to dodge bullets, right? He won't have to. So in this case, friction is something that is always working against motion. So that is a very, very common cause for negative work. And then we have potential energy. And I'm going to specifically just talk about gravitational potential energy, but it would apply to springs as well. So if an object is being lifted up or put down, the work is equal to the change in potential energy, specifically gravitational potential energy. But yeah, okay, so there's this upward force as the object is moving upwards, and then there's still this upward force as the object is moving downwards. And in both cases, the force being upwards, but sometimes that's in the same direction as motion, sometimes opposite direction. So same direction, that means positive work. Opposite direction means negative work. So you need positive work to lift an object up and negative work to lower the object down. We talked about that. That's good stuff. So where does this energy go? So if you recall, we had an example earlier on where we have a ball falling. We said it was a 10 Newton ball. It started from 2 meters up, and ball falls down, and all that gravitational turns into kinetic energy just before hitting, right? So, yeah, that was awesome. That was great. Physics, conservation of energy, love it, love it, love it. Okay, well, what happens when the ball actually hits the ground? You say, yeah, it hits. It's got this much kinetic energy, right? Yeah, well, sure, but then what happens to that kinetic energy? Because the ball doesn't bounce up to as high as it had been before, right? So what happened to that energy? Well, we had some energy transferred into the Earth, and that did cause the Earth to move a little bit negligibly, but technically there is some motion. You just can't really tell because of the Earth's giant mass. And then some mechanical energy is, and we know about this because of conservation of momentum, by the way. But then we can also talk about, yeah, some mechanical energy is lost in other forms, such as sound, heat. So you hear the ball hitting. If the ball kept hitting, you would actually feel the ball get warmer. And there is also the deformation or the destruction of the objects, in the mountain, right? So he said, well, how can we measure those things? Well, that's actually pretty difficult to measure. The easiest way of doing it is just saying, hey, what is my energy, mechanical energy, right before the impact, and then what is it right afterwards? And then just subtract. We say final minus initial. Oh, the change in. Yeah, okay, yeah. All right, that's the easiest way of seeing how much we'd say waste energy was there. And another question I want you to be thinking about here is, why is the first hill of a roller coaster always so tall? Oh, it's to make it exciting. It starts off really exciting. Well, sure, absolutely. But can the next hill be just as tall or even taller? Thinking in terms of conservation of energy, as well as outside forces, so therefore the work energy theorem, why does it make sense that the first hill pretty much has to be the tallest of all the hills for this roller coaster to work out? Okay, then we'll do some problems and do some calculations. It's good stuff, but it's important to understand the concepts first. Physics.